Today we're going to talk about the gamma method. I'm Justin Shaw, and I'll be presenting. So the motivation here is that researchers who are interested in physical phenomena often study these through time series data sets, which is to say data sets consisting of parallel time series. And an example of this would be, let's say that you're interested in internal waves in a lake. You go out and you drop one of these data buoys off the side of your boat with a thermistor chain on it, and the thermistor chain samples the water column, producing this set of time series, one at each of these thermistors, of course. And then you go back and you get the data buoy and you take your time series data set, and then you go through and you look for time periods, which we'll call features, time periods of interest, and identify any time when something interesting was happening. Right? So often by some ad hoc method, with the hope that the waves you're interested in, let's say, or the change in the density profile are evident at those times, right? So you're trying to use the sampling from the time series data sets you've collected to identify time periods of interest, which hopefully contain the phenomena of interest, right? So all that just to say, you use the data to try and help you study what you're interested in, and to do that, you have to look for some time in the data set where that phenomena is manifesting itself and being measured. Okay, so the problem with this is that many researchers now find themselves with a great deal of data because, of course, everybody wants better data, right? Higher quality in both resolution and in fidelity. And so that's great that you get better data, right? But it's larger, right? You have more time series, they're sampling more often, they're more accurate, and so on. And so you have a higher quality data set, but along with that comes the fact that your ad hoc methods that you're using to identify features, those methods don't generally scale to larger data sets. So automated methods for feature identification are needed, right? It's easy to look at 5 time series and figure out what's going on, but if you have 500 of them, you might need another way of looking at things, right? You might need something a little bit more sophisticated. So why not use existing methods? Well, you can use empirical orthogonal functions, and we will in the error map method, but they're variance maximizing, and so it takes a little bit of nuance, right? So high total variance in an EOF may be the result of an event, or it may be the result of low variance over the entire record. So there's a little more to do there, and we'll do it, but in a different video and for a different method. Wavelet, Fourier, harmonic, and spectral analysis. These are, of course, all great, but they are frequency dependent, and they're not really allowing for aperiodic or anomalous events. And they're also not designed for the analysis of many time series at once, right? So not ideal, not going to use them. Statistical methods are great, but they apply in every context because they ignore context. And so we wanted a method where researchers could use their domain knowledge, and unless they know how to encode that knowledge for use in a statistical model, the statistical methods, again, while valuable, are not going to be helpful for the process of identifying features. Okay, so the key observation is this. Since we've said we're not going to do those other things, what are we going to do? Well, let's look at a tropical storm Irene, passing a meteorological station. And we can see the west wind, south wind, and the low pressure anomaly. And so these are basically perturbations from a background state, right? So we expect physical phenomena of interest to impact multiple physical quantities nearly simultaneously, right? So when the storm goes by, we expect this. We expect something like a west wind and south wind and low pressure anomaly all to be different from their background state. So the idea is we're going to identify features in data set that are worthy of further study by looking for simultaneous perturbations of the time series in the data set, right? So if I was looking for a storm, it's a good idea to look for times when everything's different from normal. So everything's different from normal in this green box, but let's look at a particular time. We can see that there's different size of perturbations from this background in each case, but consider this. At a particular time, right here, if the smallest perturbation of all the time series is still large, this indicates a feature worthy of further study. And the reason for that is that if the smallest perturbation is large, that means every other perturbation is bigger than that. That means that everything is perturbed, right? If the smallest perturbation is still large, that means everything is perturbed. And so we can see at this point right here, we have red and orange and blue, but blue is still considerably perturbed from the background. And so the smallest perturbation, which is blue, is still large. And sure enough, it indicates a time when all three of the series are deviating from their background state. So what are we going to do? Well, we're going to take the time series that we're given, and we're going to do this process where we find the smallest perturbation at every time. We're going to do that at every time, okay? So we're going to take the minima of all the perturbations, okay? We're going to take the minimum curve across all of the perturbation curves. And then we're going to look for maxima in that minimum curve. So if the minimum perturbation across time series is still large, all time series are perturbed, and we expect to find a feature worthy of further study. Right? So we're going to do this process of finding the smallest perturbation at every time. We're going to do this look around at every time output, and then for that minimum curve, wherever it's largest, that indicates a time when even the smallest perturbation is large, which means that something must be happening. Okay, so here's the mathematics of that idea. So for each time series, you form this perturbation time series, which is the time series subtracted from the background state and scale as necessary. This is the absolute deviation time series. Okay, so large values correspond to perturbations from the trend. So for each of these time series, it has a large value if it's far from the trend. Events cause perturbations in all series nearly simultaneously, so we're going to define gamma to be the minimum of all these deviations. If gamma is large, all series must be perturbed. Okay, and so maximum of gamma correspond to times of simultaneous perturbation. So it's the same concept, done at every time. Here's just the mathematical description of it. Here's the algorithm. I won't spend too much time on that. You can look up with the associated paper. You can look up the you can literally download the code, right? So here's the algorithm, but you can download the code. Okay, so what's good about the gamma method? Well, it's computationally inexpensive. Like, that's an understatement. It's tremendously inexpensive. It'll probably take you longer to load your data than it will to run the gamma method, okay? It's very flexible. You can adjust the constants as needed. We typically go with the maximum of the individual perturbation series, but if you had another reason to do something, you could do it. It's transparent. This is one of our favorite aspects of it. Transparency is very important if you want the people who are using it to know what it is that it does, right? So this is the ultimate non-black box, okay? So it's not particularly complicated mathematically, but you do know what it's doing, right? In sharp contrast to many other methods that are available. Because it's transparent, it's easy for even non-specialists to modify, right? If you understand what it's doing, it's a lot easier to change it. It's physically motivated. The entire argument was based on physics, not really on mathematics. This is very helpful because most people who are studying these things are studying the physics of them, right? And so it's helpful to have a method that's motivated from your domain rather than from the ether. And it's very widely applicable, right? So it'll apply to any time series data set where it's reasonable to assume that simultaneous perturbation is of interest. That's a broad statement. So let's give an example. This is Monterey Bay, California. This is from Walter et al. 2016. These are observations of nonlinear waves. And so we have these ADCPs, and we get all kinds of information from them, from the CTD, of course. And so I'll refer you to this, but it's in California, and we have these thermistor chains, and we or sorry, not thermistor chains, but from that collection array, we end up with these data sets, right? So here's density, and here's kinetic energy. So that's the top and middle. And so we decided to use as indicators, what are our time series going to be? Well, there's 35 time series in depth in both rho and kinetic energy. And so we could totally do the gamma method on 70 time series if we wanted. But we decided it would be just as good for our purposes, and probably better because it's easier to visualize. Instead, we're going to do the depth averaged density and the depth averaged kinetic energy. Okay? And in the bottom here, we have the gamma method. So this is the perturbation from the mean of the depth average density and the depth average kinetic energy, right? So using the same hat notation as we did before, where rho bar indicates depth averaging, as does KE, and then the hat is the perturbation, as we saw on the mathematics page, right? So we'll just go back to that quickly. I'm forming this series right here. And then gamma is the minimum of those two curves. And we end up with the following features, right? So feature 1, feature 2, feature 3, feature 4, feature 5. So here's the order: 1, 2, 3, 4, 5. So the features in order are frontal crossing, studied in Walter et al. 2016, right? So their paper studied a frontal crossing, and sure enough, using our method, the most important feature identified is the thing they studied, which is right here. Okay, so you can see this large upwelling event, the frontal crossing event studied there, along with the kinetic energy. 2 internal wave and frontal crossings, right, which would be the second and third right here, and you can see those right here. Okay, one's right at the end of the time series. A large upwelling. Okay, so that's blue right here. There's a upwelling right here. This one's kind of a cool one because it's not as obvious in the density, but of course it's very strong in the kinetic energy. And then a cross-shore pulse of cold water. Okay, this one is right here. And it's interesting because it doesn't pop out visually, but mathematically speaking, it is there. Okay, this shows a lot of. This example shows a lot of valuable things about the gamma method. The first one is that it discovered what they discovered by ad hoc methods, right? They looked at this and said, oh, this is interesting. But actually, the gamma method shows that, yes, it is interesting, mathematically speaking, and could have been identified this way. Even if the data set was so big that you couldn't look at it in this way, okay? But then we also go on to rank order and identify some other things of interest. And this fifth one doesn't pop out at you. So no one's going to look at this set and go, oh, right here is where it's important. But the gamma method says, actually, in a mathematical sense, this is relevant, right? This is a large cross-shore pulse of cold water, right? So the point of this presentation is not to analyze every piece of data. The point of identifying features is to tag places where you might want to look, and then wherever the analyst would like to look after that is up to them. And the gamma method in this case says, well, you might want to consider this. Okay, here's another example. This is the Chen cave system. So a cenote is a situation where basically it's a freshwater pond that is attached to the ocean through an underground system of caves, right? And so what that ends up being is a situation where you have fresh water on top, and then you have salt water underneath, and of course you have this transition from fresh to salt water. And the reason why you'd care about this, I mean, besides the fact that it's interesting, but in a logistical sense, if it rains, it mixes this, and suddenly you don't have fresh water to drink. Okay, so that's one of the reasons why people are interested. And so here we have the density, salinity, and temperature sensors. There's just three, right? So here is the set of sensor locations, and it's just one little module that's got 3 time series that are being recorded, right? In sharp distinction with the 70 that were being recorded in the previous case. And so we have density, salinity, and temperature. And we run the gamma method again, and we find the following. Features in order are Hurricane Nate, Hurricane Philippe, Hurricane Earl, Hurricanes Irma and Jose, and then several other storms. Okay, so the point is, you run the gamma method, and it again identifies things of interest right away. It's very effective at doing so. Okay, so the gamma method summary. The method allows the analyst to use their knowledge of the physical context. I've brought this up a couple times, but what this means is that it is not another black box. It is a tool that can be used by everybody that has a little bit of mathematical training. They don't have to be a mathematician. If they've taken their undergrad stats course and understood it, there's nothing keeping them from understanding the gamma method and how to modify it to their context and get something good out of it. The method identifies features previously identified by ad hoc means. That was the Walter et al. Example. But it also identifies, which is the Monterey Bay example. But it also identifies more features worthy of study, right? Which is the other features besides feature 1 in the Monterey Bay set. It's applicable to a huge variety of contexts, including but not limited to iTrax cores, shale and delta, GFD, computational fluid dynamics, atmospheric readings, and so on. Okay, these are all physical examples, in a way, including computational fluid dynamics, right? But again, if you had a set of time series whose simultaneous perturbations were of interest, you could still apply this. And currently we have projects using the method to identify volcanic eruptions, tidal and rain events in cenotes, and temporally under-resolved features in CFD runs. So that's the gamma method. We're very excited about it. We have multiple people and in many locations using it. And that's a summary for now. I encourage you to check out the paper itself. And thanks for listening.